Hello, welcome back. In the last section, we discussed some sub areas of AIOps research. So in this section, so we will discuss some common techniques used in AIOps practice and research. Okay, uh, so we will discuss techniques including clustering, classification, frequent pattern mining, associated rule mining, and dimension reduction. Okay. So we already mentioned that. So AI ops leverage machine learning, big data, and other analytics techniques, right? So big data techniques or usually include the techniques like the tools like Hadoop, Spark, Elasticsearch. So these are tools that can handle big data. Okay. So classification of machine learning usually include regression, classification, clustering, right? The first one um, we want to discuss is uh, what what are the different types of machine learning, right? I The first type is supervised learning. So what is supervised learning? I so the object in the training data have labels. For example, if we want to classify the type of fruit, whether it is an apple or pear or a banana, right? So we want to classify them into these different types based on their shape, the color, the taste. Okay, in supervised learning, so in the training data, we have a training data, the training model. In training data, we know which one is apple, which one is pear, which one is banana, right? Then after we train the model, we apply this model to the new data. In the new data, we don't know which one is apple, which one is pear. We just know the features include the shape, the taste, the colors. Okay. So what is unsupervised learning? Unsupervised learning, we don't have the labels, right? We don't use a label to train the model. Actually, we establish the existence of classes or clusters based on a set of measurements observations, such as the taste, the color, uh, the shape, right? We use these things to group things together, for example, but we don't know whether it's apple or it's a banana. So this is unsupervised learning. The only difference, do we know the label or not? Do we use the label or not in a training process? Okay. So one example of supervised learning is classification. So one example of unsupervised learning is clustering. Okay. But classification is usually a two-step process. The first step is a model construction. In model construction, we want to train a model. So we want to train a model to describe a predetermined classes. This model should be able to describe the predetermined classes. We have a training data set. The training data set we know the class, the label of each data instance, and we have the features. Each data instance is called a tuple or a sample. Okay, so this tuple or sample has a label or a predefined class. Okay, so examples include we build a decision tree or build some classification rules, right? So this is the first step to model construction. The second is model application. After we construct a model, we want to apply it to unseen objects, to future objects. Two sub-steps. First sub-step is to estimate the accuracy of the model, right? We want to estimate the accuracy of the model using an independent test set. This is independent from training set. Right? After the estimation, we think the accuracy is good enough. Then we apply the model to classify the samples with unknown class labels in the future, right? So this is a two-step process of classification. Let's see an example, a simple example, right? Model construction. In the training data, as we know, this is supervised learning, right? Classification. In the training data, so we have for each row indicate one professor, right? And include the name of the professor, the rank of the professor, how many years the professor works in the university, right? The label or the class, the one we want to classify is whether the professor is tenured or not, right? So how can we do it? So we want to use the name, rank, and years to determine whether the professor is tenured or not. So we build a model, construct a model. So this model is very simple. This model is a set of rules. If the rank of a professor is professor, or the year is greater than 6, then the tenure status is yes. So it's a very simple model, right? Then we'll apply this model, right? We'll apply the model to unseen data. We have unseen data whose name, professor name is Jeff, rank is professor, and the number of years is 4. Based on the rule we have just seen, right? Because the rank is professor, even though the year is less than 6, the rank is professor, so tenure status is yes. This is how we construct and apply the model. This is a classification model, okay? We see here we have different types of data, right? The name is not some data are not numbers, right? Name is not a number, rank is not a number, year is a number, tenure is not a number. So we have different types of data. So the different data types in supervised learning, so shown in this figure, right? So there are typical types of data. The first category is a categorical data. Second category is numerical data. In categorical data, we have binary, nominal, ordinal data. In numerical data, we have continuous discrete data. For binary, it's easy, true or false. Nominal data, like the name of the professor, right? Or like English, French, Spanish, a different language. Ordinal data is similar to nominal data, but there's an order, like a beginner, intermediate, advanced. They are nominal data, but they have an order, right? So they're called ordinal data. Continuous, the height, the weight, right? Discrete data. So yeah, it's similar to continuous data, except that it's discrete. How can we handle these different types of data in a model? The first approach is to select the machine learning model that can handle this type of data naturally. For example, some models cannot handle categorical data, like linear regression model. In this case, you need to convert the categorical data into numerical data. So we'll discuss how we can do the conversion later. Like some models can handle categorical data. In this case, you can just use this categorical data, right? There are many different types of model that have different requirements for the data format. Okay, so in order to use the right to handle the right problem, use the right model, just check the requirements of the model. Okay, and we know that many models they have the requirements that they only accept numerical data. So how can we convert categorical data into numerical data? So there are different there are different approaches. We call them encoding approaches. How can we encode categorical data into numerical data? right? Normally, we would consider a nominal data and the ordinal data. How do we encode nominal data and ordinal data into numeric data? Because for binary, it's very simple. Binary is true or false. We can just use 1 to represent the true, 0 to represent false. That's very easy. How to encode nominal data and ordinal data into categorical data, into numerical data? I can do this. First one is a ordinal encoding, right? Ordinal encoding can convert ordinal values to integer values based on their natural ordering. For example, we can represent beginner as 1, can represent intermediate as 2, advanced as 3. This is ordinal encoding, but ordinal encoding cannot apply to everything. You cannot apply ordinal encoding into nominal data, right? You cannot use 1 to represent Mike, 2 to represent John, right? 3 to represent Smith. You cannot do this because the nominal data, they don't have order, but your numeric data have the order. You cannot do that. Another way is one-hot encoding. Right? So one-hot encoding, we create one binary variable for each possible value of the encoded variable. For example, weather. Weather is a nominal data, right? Categorical data, nominal data. So weather can be sunny, rainy, right? And other types of weather. If we apply one-hot encoding, we create one binary variable for each possible value. So we create one variable for sunny. Here we use is sunny or not, right? So if it's sunny, we put is sunny as 1. If it's not sunny, put is sunny as 0. Similarly, we create a binary variable for rainy, right? Is rainy here. This is one-hot encoding. And we have dummy encoding. In dummy encoding, so we don't create a binary variable for each possible value of the variable. Actually, we create a binary variable for n-1 possible values of the encoded variable. So n is the number of possible values of the encoded variable. For example, here, we only create a binary variable for sunny. We don't need to create one for rainy. We create n-1. Here is 2 minus 1. Because if we know it is sunny, then it is not rainy, right? So this is called dummy encoding. Third way is a target encoding or likelihood encoding. Still here, we have two variables, room A and room B. For each room, we know the number of nodes in the room and number of field nodes in the room. And we want to predict whether the room is associated with a finger, right? How can we do it? We associate this feature with the target, right? We will create a value for this feature based on its relationship with the target. Here, target is the finger, right? Where there's a finger. For example, here for room A, the number of nodes is 300. The number of field nodes is 30. So the percentage, the likelihood of a finger is 0.1 is 10% or 0.1, right? So we assign the value of 0.1 to room A, and similarly we assign the value of 2.2 or 0.2 to room B. This is targeted encoding. Okay. So how do you apply to AIOps solutions? So yeah, for example here, so we want to predict the log level of a logging statement, right? When you write a logging statement, we want to predict the log level. So what can we do, right? Log level can be fatal error warm info debug trees, right? So here, this value is fatal error warm info debug trees. So they are ordinal data, right? So we need to, the first step is to find the right model which can handle ordinal data. If we cannot, then we encode this ordinal data into numerical data. Fortunately, we can find a model. There's a model called ordinal regression model, which can handle ordinal data. So we just use this ordinal regression model. I think I accidentally stopped the sharing. Okay. Okay. Okay, it's back. Yeah. So this is a classification, right? So the second technique we want to cover is clustering. So what is clustering? The clustering is a process of grouping a set of objects into classes of similar objects. So here in this figure, you can see that different dots, right? Each dot you can consider as an object. So clustering is to group them into different groups. In order to cluster data, right? So we need to find the similarity between the different data points, right? We group similar data points together. But what is similarity? Similarity is a quantity or state of being similar. It's about likeliness, resemblance, or a similarity of features. Okay. So usually we determine a similarity based on the similarity of features, because this is one that we can measure, we can quantify. Okay. So how to determine similarity between data points? How to determine the similarity of features? For example, we have two vectors, x and y, right? And then this vector is, you consider vectors as a vector feature, right? How to calculate the similarity between x and y? So one way we can use a Euclidean distance, right? This is the simplest way to calculate the similarity between two vectors or two feature sets. The second way we can use a correlation distance, right? Or cosine similarity. So we can consider the correlation between these two feature set or two vectors, right? There's different ways. There are different ways to calculate similarity. So based on similarity, we can do clustering. Okay. Two types of clustering. So one type is hierarchical clustering. Second type is partitional clustering. In hierarchical clustering, I'll first look at the partitional clustering. We just simply cluster the different objects into different clusters. The different clusters, they are at one level. There is no hierarchy. In hierarchical clustering, so there are different hierarchies, right? For example, the first hierarchy can be of clustering can be male and female, right? So under female, there will be senior female and younger female, right? Under male, there can be a senior male and junior males. This is a hierarchical clustering. I'll use one example to describe what is clustering, how it works. So here, the example we'll use is k-means. K-means is a simplest and a very popular clustering approach. How k-means works, right? So if you look at this here it shows the algorithms, but we will just skip here. I will go to the visualizations. Okay. So k-means. So k-means is a clustering approach. We want to group these different data points into clusters, right? How many clusters we want to group? You can choose a number of clusters. Here we will choose 3. We want to have 3 clusters. How can we do it? First step is we just specify 3 points here, right? Each point will represent one cluster, right? Then we would assign all the data points into these three clusters based on the distance between the clusters. And here, K1, K2, K3, we can consider as the center of the cluster. We can assign all the data points to the three clusters based on their distance or their similarity with these cluster centers. After we do the calculation, we find that for each data point, which cluster center is the closest. Then we assign all those data points into these three clusters. Okay. Then we find that K1, K2, K3, they are not actually the cluster centers. So then we move these 3 points to these cluster centers, right? We move them to the cluster centers, actual cluster centers. Then we recalculate the distances between the data points and the cluster centers. And we reassign these data points to these three clusters. We find some points change the clusters because we moved these data cluster centers, right? Then we repeat the process. We move K1, K2, K3 again to the actual cluster centers. And then we reassign the data points to the clusters. And there's no change. If there's no change at all, we finish it. And we get three clusters, right? This is the process of a k-means clustering process. It's a very simple process, right? So how clustering can be applied to AIOps, right? I remember we had one example in the previous section, right? So we cluster time slices in order to determine like which time slices will have memory problems. We cluster time slices into groups, right? Remember, so we cluster them into groups based on the similarity between the log activities. So then we can look at a smaller number of groups instead of look at all the time slices. So that's one application of clustering to AIOps solutions. Okay. The next topic we'll discuss is frequent Python mining. What is frequent Python mining? So frequent Python mining is about finding the sets of items frequently occurring together. Okay. For example, there are different customers, so they buy some items together, right? So some customers that would buy beer, nuts, and diaper together. Some people would buy beer, coffee, and diaper together. Some people buy beer, diaper, and eggs together, right? So the goal of frequent Python mining is to find which items always purchase together, right? Frequent Python mining. So there are some concepts like a item set. So item set is a set of items, right? And support, right? Support is how many times these two items or these three items happen together. How many times one item set appears, right? So what is a frequent Python? Item set X is frequent if X support is no less than a minimum support threshold. If we, for example, if we determine the threshold as 3, then all the item sets that appear 3 or more times are frequent items. So if you look at this example on the left, we can see that beer and diaper always appear together. They appear together for 3 times, right? So if the threshold is 3, then beer and diaper, it is a frequent item, right? So how can we use these items, this frequent Python mining, frequent item set mining? Is we can, for example, if we want to place these items in the grocery store, right? So we can place items, the frequent item set. We can, based on a frequent item set, we can place things together. For example, we can always place beer and diaper together because people always buy this two things together, right? That's how we can apply frequent pattern mining. Also, it can be applied in AIOps solutions. We will see example later. Another techniques related to frequent pattern mining is association rule mining. Associated rule mining is not to identify frequent patterns, but to identify giving one item to measure the possibility that another item appears. For example, giving beer, what is the possibility that there will be a diaper that is also purchased? This is association rule mining. First, to find other rules. For example, when people buy beer, they also buy a diaper. When people buy diaper, they also buy beer. To find other rules. Then to calculate support. Support is a probability that when people buy A, they'll also buy B as support. Right. Sorry. Support is the probability that a transaction contains both A and B. That's support. Confidence is the probability that when people buy A, people also buy B. Okay? And then we can calculate the minimum support and minimum confidence. We can set this threshold, and we can calculate the support and confidence of different rules, and then we can identify the frequent rules. For example, so when people buy beer, they also buy diaper, and the support is 60%, the confidence 100%. So this can be a rule that we found. Okay. Associated rule mining can also apply to AIOps solutions. Okay, let's see a concrete example to illustrate how it applies to AIOps solutions. In this example, so the researchers use frequent pattern mining to detect anomalies in system logs. So what is frequent pattern? Because there are lots of logs in the system, right? So log A, log B, log C. So they always find log A and log B always happen together, right? These are frequent patterns. And then they find in other logs, B and C happen together, but it never happened in other cases. So B and C are rare cases. This item set is not expected. This is not a frequent pattern. If this is not a frequent pattern, then something is wrong. So we can use this way to identify anomalies. That is to apply frequent pattern mining to detect anomalies in system logs. Okay. Another technique is dimensionality reduction or dimension reduction. So in monitoring data, there are lots of data types, lots of data sources. For example, you have CPU, you have memory, you have throughput, you have many types of data. So how can we deal with this large dimension of data, right? Like here, we have performance metrics, we have logs, all this data, right? So if we want to examine the data one by one, so the error is very large. Can we reduce the dimension? Yes, we can, right? So there are dimension reduction techniques. So one example is principal component analysis. What is called a PCA? What is PCA, right? So PCA transform a set of correlated variables into a reduced set of uncorrelated variables. These principal components. These uncorrelated variables are principal components. So each principal component is a linear combination of the original variables, right? So in this way, we can have a smaller number of PCs or principal components that can explain the variance of the original variables. For example, here we have two dimensions, X and Y, right? We have 3 data points. If we do a rotation of these 3 data points, we can rotate them into almost 1/9, right? And then we can use one principal component, PC1, to represent the data. PC2 can also be used, but PC2 only represent a small variance of the data. Okay, so this is how we can apply principal component analysis to reduce the dimensionality of the data. You don't need to understand the detailed mathematics here. You just know that principal component analysis is a way to reduce the dimensionality of the data. Okay, we see its applications to AIOps solutions. So, for example, here, in case study of an industry system at BlackBerry, we found that the first principal component can explain around 40% of the variance of all the performance metrics. There are hundreds of performance metrics, but if we just use one variable to represent one principal component, we can represent 40% of information. And if we use a full principal component, we can explain 80% of the information. Okay, this is a visualization of how it works, right? This is another way to do a correlation analysis to reduce the dimension. We can measure the correlation between the variables, and we reduce if two variables are very highly correlated, we reduce one, right? In this figure, it shows the correlation between the variables. The bridge connecting two variables indicate their correlation. If there's two variables, it's correlation like close to 1, right? That's very high correlation. So we can remove one and keep one. So here, the dotted red line can show a threshold to cut off, to only keep one variable below this line, right? Okay, that is another way of dimension reduction. There are other ways of dimension reductions like TSNE and LDA. So we don't go to details later. If you are interested, you can have a look at, you can do a search and find the definition. Okay. So that is the common techniques used in AIOps solutions. There are many other techniques, but these techniques are pretty common in different AIOps solutions. Okay, so here are two small exercises. Okay, the first one, I'll first go over these two exercises, and I will ask you to vote. Okay, the first one is this is to select the most appropriate techniques for different scenarios. First, so your monitoring data recorded the user behaviors, such as browsing items, purchasing items, right? In an e-commerce system, you want to find the patterns of user behaviors. For example, browsing item A following a purchasing item B. Which technique will you use? And the second exercise is given the more, yeah, I think which one is, yeah, given the monitoring data of a large-scale software system, so you want to estimate whether there is a runtime failures in the production environment, which technique will you use? Classification, clustering, frequent pattern mining, or associated rule mining? Okay, so we use menti.com, right? So let me share the browser. Okay,